Okay, so far we discussed about capacity. And last class I told you how the capacity is obtained, or the capacity curve is obtained using nonlinear analysis on computer. That means making use of numerical methods. Okay. So what we have discussed in the class and what you have done in the assignment, that is approximate method which is suitable for hand calculations. If you have to do numerical calculations, okay, on a computer, then the method is slightly different. Okay, where you do a step-by-step solution, and ultimately you get a curve between base shear and delta roof. In case of a building, it will be in terms of base shear and roof. In case of a bridge, also similar curve can be obtained, but you have to identify a representative point where you can monitor the displacement. In case of a building, the roof displacement is fine, okay, but in case of a bridge, there is no roof. So you have to identify some point, okay, which is representative of the displacement. Okay, but we need one point, displacement at one point, then only we can plot a graph. If I am considering displacement at several points, I can't plot. So I need one representative point, which we also call monitoring or monitored displacement point. The point where you are monitoring the displacement. So you can get for any structure for that matter a curve, and this curve we call capacity curve. But so far we have not talked about the demand. Okay, so demand will come from earthquake. We have not talked about earthquake. So demand comes from earthquake shaking. And this we call hazard. So today we will talk about seismic hazard. Hazard due to earthquake at any site. You must have heard this word and might have been taught in some other courses also. So can you define me what is seismic hazard? We also discussed it. Some discussion we had in the last semester. You are hearing this term again and again. So what is seismic hazard? What we call seismic hazard? If I ask you to define seismic hazard in your own language, how you are going to define? For example, suppose I want to do design of this building. Okay, so you need capacity and you need demand. Demand is given by the hazard. So how you are going to quantify the hazard for this building? Probability of occurrence. Okay, so this is the most common definition which you will hear. It is a probability. Suppose the probability is 40%. Can you design building for 40% probability? How will you design for 40%? Will it help you in any way? So hazard is not probability. Remove this definition from your mind. Okay, hazard is not probability, because what you can do with probability? Can you design a building or you can analyze a building for just probability? If I tell you probability, so hazard is not probability. Then what is hazard? Amount of damage. But how will you get amount of damage for this building? what you are going to do with this amount of damage. So amount of damage is also not hazard. So there is a lot of misconception about hazard. I want to remove that. It is not probability, it is not amount of damage, it is something very simple. What is that? So what is hazard? It is not damage caused by earthquake. That is not hazard. That may be loss. Okay, that may be damage. That may be risk. If you are talking in future terms, then it is risk. If it has already occurred in an earthquake, it is loss. Okay, so that is not hazard. So what is hazard? Answer lies, if you have to design this building or analyze this building, what do you need to analyze this? Amount of load. And in case of earthquake, I told you earthquake is not applying any load. So how earthquake is applying load?
Energy in terms of energy.
In terms of energy. Okay. So it can be in terms of energy. Okay. But how to quantify energy? There is a problem. Energy can be hazard. Okay. If you know energy, how much energy is going to be imparted to my structure, I can design my structure for that. But how to measure energy?
I need to measure the velocity of my structure for that particular energy. Then I can quantify my energy in terms, like by energy conservation principle. One is applying energy, that energy is converting to other. That is maybe potential energy.
Yeah, but the problem is that in case of dynamic problem, when vibrations are occurring, the energy depends on the frequency also. That's the problem. So energy can be used. I am not denying that energy cannot be, but it is not the most common measure of hazard. How you are going to measure the hazard? If I ask you, this is the site where I want to construct my building, which instrument you will put to measure? Intensity of damage. Why you are saying intensity of damage? Damage will occur when I will construct my structure and earthquake will occur. And suppose I design my structure nicely, there will be no damage, so there is no hazard. So damage is not hazard. It's something very simple. It is level of ground shaking. Okay, and because it is going to occur in future, I do not know, it is not occurring all the time, so that I can measure and see what level of shaking is occurring. Suppose the ground was continuously vibrating, then the life would have been very easy. I would have put a instrument and measure what vibrations are occurring, and I will design my structure for that. The problem is that it will occur sometime in future. I do not know. So I have to go for expected level of ground shaking. Okay. When you say expected level, there are two possibilities. You can say that an acceleration of this much 0.5 g will occur. Okay. So this is deterministic. I can say that expected level deterministic. Okay. So in case of deterministic, you will give one value. But this is the level of shaking which is going to occur. But it is having a lot of uncertainty. We can never be certain. In fact, we cannot be certain even about the strength of the concrete. You have seen the concrete strength is also varying. So how can I be certain about the level of shaking which is going to occur at my site? So I will never be certain. I cannot give a deterministic value 0.5 g or 0.5123 g. I can't say. So there will be a probability. Okay. So we explain in terms of probability of accidents. Let us say that level of shaking which will be exceeded 5% times. The level of shaking that will be exceeded 50% times. The level of shaking which may be exceeded 75% of time. Okay, so I will assign or I will get levels of shaking corresponding to different probability of accidents. Okay, so when we define characteristic strength of concrete, we say 95% confidence strength is 25 megapascal. So when I ask you what is the strength of concrete, you don't say 95%, you say 25 megapascal. But actually it is corresponding to 95% confidence. Same thing is here, hazard is not probability. I can define hazard corresponding to different probabilities. I can say 95% confidence, 50% confidence, 84% confidence, like that. So the probability comes there. So probability is not hazard. Hazard value can correspond to different values of probabilities. In case of characteristic strength of concrete, all over the world it is fixed 95% confidence. But in case of hazard, there is no such consensus. Okay, there is variation and we will talk about that variation. So different probabilities can be assigned and accordingly there will be different levels of ground shaking. If I am considering a very frequently occurring earthquake which can be exceeded lot many times, then the level of shaking is going to be low. If I am considering an earthquake which will be exceeded rarely, okay, then intensity will be high. But probability is not intensity, probability is not hazard. So keep that in mind, hazard is not probability. Hazard can be expressed for different probabilities. Okay, so it is the level of ground shaking which is hazard. So then the question will be, how can I measure and express level of shaking? Level of shaking is a qualitative term. So how we can express level of shaking, how we can measure level of shaking? You already know what are the instruments to measure earthquake? Seismograph and accelerometer. What does seismograph give? Velocity. Accelerometer gives acceleration. When the instruments were not there, then how it was measured? Even then the ground was shaking. Okay, and you have to express that in some terms. You have to measure in some terms. Okay, so that was what we call subjective measurement. For example, if you are expressing level of shaking, oh, it got very high. So different people will mean different thing by saying very high. So there has to be some scale, even when instrument is not there. What do we mean by very high? What do we mean by moderate? What do we mean by slight? Okay, so for different levels, different quantification was done, and that was in terms of damage. Caused by earthquake. So that was measured in terms of damage caused by earthquake. It is not damage. So keep in mind, if you have nothing to measure, no instrument, how you are going to assess the level of shaking? How you are going to define the level of shaking? So at that time, the only way was to observe the damage. So similar type of building in this earthquake got 90% damage. Similar type of building in that earthquake got 20% damage. So you can say that relationship between those. Okay, but where buildings were not there, suppose the earthquake came in an area where there was no building, then we cannot measure. Okay, there has to be something on which I can see the effect. Okay, so I can see the effect on buildings, I can see the effect on slopes. So some man-made or natural structure has to be there if instrument is not there. So that's why earlier days, these subjective scales or what we call intensity scales. You have learned different types of intensity scales. So these intensity scales are nothing but trying to remove subjectivity. These are subjective scale because these are based on manual observation, and when you are doing manual observations, there are chances of variation. Okay, so to minimize those variations, so that if two persons are observing the same area, they should come to same level of shaking. Okay, so for that, the rules were provided there that how we are going to measure that. So that gave rise to intensity scale. So intensity scale were used when instruments were not there, and if no structure is there, there is a flat ground, okay, no building, no slope, okay, you can't, nothing will happen. But that doesn't mean that the shaking did not occur. Shaking occurred there also. Okay, so hazard is there even if damage is not there. Even if no damage has occurred, doesn't mean that intensity of shaking was zero. Because nothing was there, so nothing got damaged. So hazard is there even if there is nothing in that area. This is another tricky question. People ask that suppose earthquake occurs in an area where there is no population. Will there be any hazard? There will be hazard. There will not be any risk. Okay, because what will earthquake do? Even if it causes severe shaking, what can it do? Nothing is there. So risk is not there, but hazard is there. So hazard is just level of shaking, whether your building is there, your building is not there, whatever level of shaking is there, that is hazard. Now we have instrumental measurement. And the problem is that instrument also you cannot keep everywhere. Okay, and even if you have kept instrument, earthquake may or may not come during that time for which you have kept the instrument. Okay, so instrumental measurement is not possible everywhere. Even when earthquake occurs, okay, there will be only few locations where instruments are there which will be able to record the earthquakes. What at other locations? What can we do? For example, earthquake occurred in Turkey. You have seen a lot of damage. It's not that every 100 meters there is an instrument. You can't do that. So instruments will be only at few locations, and there will be some locations where there is no instrument. What we are going to do at those locations? We don't have any other option than going for subjective measurement. So this subjective measurement we started when instruments were not there. But now also we are using those wherever instruments are not available. But we can better correlate those with instrumental measurement. At those locations where instrumental measurements have been done, the instrument was functioning, there I have got the measured level of shaking. Okay. And at other locations where instrument is not there, I will correlate it with the damage. So this intensity scale or correlation of intensity with damage is still a useful method, okay, because we cannot put instruments everywhere. Okay, and my problem is not only to measure the earthquakes which have occurred in the past or which are occurring, I have to estimate the level of shaking which is expected at my site. Okay, so how we can get the expected level of shaking. So for expected level of shaking, I have to do seismic hazard assessment or seismic hazard analysis. Okay, there is a course also on seismic hazard assessment. I don't know if any of you are doing that. So there is a full course on seismic hazard assessment. I can't cover that much, but I will give you only some idea that how seismic hazard assessment is done. And then there are two methods of seismic hazard assessment. One is what we call deterministic. In short, we call it DSH. So, as I told you, DSH will give you one value of hazard, that the level of shaking at this space is this one, 0.5 G. Okay. But that will not be reliable. Why it will not be reliable? That whatever calculation I am doing, I am using so many approximations. Okay. The information, exact information is not available to me, but I am giving some value. Okay. So that appears to be very convincing. If I give you one value that design your structure for 0.5 G, designer is happy, more happy with that. Okay. But problem is that 0.5 G is not reliable. Actual earthquake may be 0.8 G, which will really come at that set. So to take that variability into account, we do what we call probabilistic. PSHA, and in PSHA we consider uncertainties and variabilities in different parameters. Okay, and its result we get some hazard in terms of probability of accidents, or what we call average return period. So we say that there is 50% probability of occurring 0.5 G PGA, okay, at a particular site. Okay. And then when we say that the probability of occurrence is, let us say, 25%, then the PGA will be high. Probability of accidents, 25%. So how much risk I am willing to take? Theoretically, whatever value I design, larger than that earthquake is possible. It can't be ruled out. Okay. But the probability of larger earthquake occurring will go on reducing. So some risk will always be there. Whatever hazard you are considering in your design, there is always a probability that higher earthquake can come. That probability you can go on reducing. And when you are reducing the probability, what you have to do? You have to design for larger value of PGA, means larger cost. So you can go on reducing that probability, which will exceed from the design capacity of your structure. Okay, that probability you can reduce, but you have to pay cost for that. So you have to keep a balance between the cost and the associated risk. So some calculated risk we always take. In case of deterministic hazard assessment, we get one value, remain confident throughout our life, but when actual earthquake comes, then it doesn't work. Okay, we don't know. Here what we do, we know that what is the probability of occurrence, what is the probability of accidents. Okay, so this is considered to be a more what we call considered approach. Okay, you know, the owner knows that there is a probability, a small probability of failure. Okay, although he will not be very comfortable with that probability, he would have been more comfortable if an assurance was given that you design for 0.5 G and nothing will happen to your structure. But that type of design does not exist. There is always some probability that my building which I have designed may fail. Okay, earthquake may be exceeded and we have to live with that. We have to communicate that. Only I should not have that guilt that what I have designed may fail. I should be able to communicate it to all stakeholders. I should tell them that we are doing the best and this much money we are spending, this we are able to achieve. Okay, if earthquake occurs larger than that, then it is going to fail. Okay, it's not a very comfortable situation, but that is the truth. So this conveys the truth better as compared to deterministic seismic hazard assessment. Okay. How to get our, oh, I can get, I think, from here.
Just click on the slide and there will be a bar.
Okay. So we discussed this. I have shown these plots to you earlier also. I have taken from Yogendra.Earthquake book. Okay. So the top one is the typical plot of accelegraph. What we are getting a record from an accelegraph. Okay. So this we call accelerogram, and it is giving us the acceleration. This is plot of a seismograph or seismogram. It is nothing but integral of acceleration. Okay, this is plot of the displacement. We can't get it from an instrument. We can get it by integration of velocity or double integration of acceleration. So you can see that acceleration is having much higher frequency of reversal. Okay, velocity has lesser frequency of reversal, and displacement has much less. Okay, acceleration finally will become zero. The ground has to stop. Velocity will also finally become zero, but there can be a permanent displacement. The displacement, there may be a net displacement. The displacement will not come to zero. Okay, so this will not come to finally zero. Now, if we look at the accelegrams of past earthquakes, there is huge variation, large variations, different types of records. Every earthquake has its unique signature. Now, my problem is that I have to design my building for an earthquake which will come in future. So, which one of these will come at my site? I do not know. So, I have to sort of guess, predict, okay, estimate which earthquake is going to occur to me. Okay, and when these accelegrams are unique, these are signatures, okay, definitely any one of those is not going to come at my site. Okay, so what will come at my site will be different than all of those. So can I find some governing parameters here which I can use to predict the earthquake which is going to come at my site? So we need some parameters in terms of which we can define the ground motion characteristics. You already know. Can you tell me what are the ground motion characteristics? So there is a set which we call amplitude parameters. Amplitude parameters are PGA, PGP, and PGD. You already know what are these. Peak ground acceleration, peak ground velocity, peak ground displacement. You have done an exercise also in the last semester. After downloading the ground motion, you can obtain how to obtain PGA, PGP, and PGD. Then we have frequency parameters. Okay, so frequency content. How we can represent the content of a frequency content of a accelerogram? So we do for that Fourier transform, and when we plot, what does Fourier transform gives us? The amplitudes and phase angles of different harmonics. So actual earthquake motion, which you have seen in just the previous slide, it is very random type. but you can represent it through Fourier transform in terms of different harmonics which have constant frequency, one frequency. Okay, and then you can get amplitude and phase angle. So if you plot those amplitude, you get amplitude Fourier spectrum and you get phase Fourier spectrum. And then the third parameter which is important to us is duration. That duration which is going to affect. So that duration also I want. You know the effect of all these three, importance of these three. What is the importance of amplitude? PGA. Larger PGA means larger inertia force on my spot. Okay. Larger PGV means larger energy particles. Okay. So what you were talking, that hazardous energy, hazardous probabilities, all those are related. Okay. But hazard is level of shape. That you have to keep in mind. So PGA, PGD, PGD, those will give you the amplitude of the motion, and larger amplitude means larger damage potential of the earthquake. We are trying to determine the damage potential of that earthquake which is going to occur at my site. So for that I need these three parameters: amplitude, frequency content. Why frequency content is important? Why PG alone is not enough? I have one earthquake of PGA. I mean, you can see in this example itself. All these earthquakes are very notorious earthquakes. Look at PG of this and this. Does it appear dangerous from any point of view? What is PG? These are plotted on the same scale. Okay? So this PGA is so many times of this, but this also caused severe damage. Why?
Large number of cycles.
Large number of cycles. Number of cycles is not large. Here you see. It's because of the frequency. Okay. So unfortunately, the frequency content of earthquake down motion is in the range of the frequency of our structures. That's the problem. Okay. Suppose this frequency was in kilohertz, ultrasonic range. Okay. So will anything happen to our structure? Nothing. Because the frequency will be so high, energy in that may be much larger, but it can't do anything to it, will not damage our structure. It will simply, our structure, it will pass, the structure will not respond to it. Problem happens when the frequency of excitation and the frequency of the structure is close, is in the same range. Unfortunately, that happens in case of us. And in some earthquakes, it matches with the frequency of a particular structure. Then the structure will undergo very large damage. Okay, that's what happened here in 5 to 20 story buildings. So the frequency content here was in the range of the period of 5 to 20 story building. So the damage was selected only 5 to 20 stories, but that damage was quite severe, although PG is nothing as compared to other earthquakes. So it happened because of the frequency tuning. So if the tuning between the frequency of the structure and the ground motion occurs, then there will be a resonance like situation. But you have to keep in mind, resonance occurs under steady state condition, you have seen that the amplitude of response develops when a harmonic motion with the same frequency is applied. So here earthquake is not having one frequency, fortunately. It is having multiple frequencies. And that frequency is changing with time also. These different pulses, these are not periodic. Okay, period is not same, it changes. So that's the good thing about earthquake, that it does not have same frequency throughout or one frequency. There are multiple frequencies, and those multiple frequencies also change with time. Okay, so this resonance does not happen. But if those frequencies are nearby to the frequency of the structure, then resonance like situation, or what we call quasi resonance, can happen. And that's what happened in case of Mexico City earthquake. Quasi resonance like situation happened with buildings 5 to 20 stories. That's why this frequency content is also important. Duration, also we discussed. What is the role of duration? Accumulation of damage. So damage is cumulative. Whatever deformation you are causing, even if it is a tiny deformation, a small deformation, even then there is some damage. Okay, and that's what we call fatigue failure. So in fatigue, what happens? That small damage goes on accumulating for millions of cycles, and finally the structure gets damaged fully. It collapses. Okay, so in case of earthquake, the displacement is much larger. In different cycles, there will be yielding. So damage is much more than what is occurring during surface load conditions. Okay, and that's why in few cycles the structure will fail. Okay, due to accumulation of damage, and this we call low cycle fatigue. We discussed in the beginning of this course. This low cycle fatigue is a crucial parameter, and low cycle fatigue will depend on the duration of the earthquake. So duration is also important. So when we are talking about the earthquake which is going to occur at my site, which I expect it to occur at my site, actually I cannot predict the actual earthquake, but I can predict these parameters. So rather than predicting actual signature, which is impossible, I can predict these parameters. Okay, so that's what we are going to learn in seismic hazard assessment.
Sir,
Yes.
use of Fourier spectrum.
Yeah.
How to means you are saying that earthquake.
Because if I show you this ground motion, just by seeing it, can you tell which frequency, which building it is going to coincide? The frequency? How you will do that? Suppose I want to know what is the frequency content of this earthquake. How I am going to know the frequency content? By plotting Fourier spectrum. So I will plot a Fourier spectrum, and Fourier spectrum will give me that in which frequency range. So a typical Fourier spectrum you have plotted also in your first semester. So any function, let us say u g double dot t, this is the ground motion, you are representing it ai sin omega I t plus phi. Okay, that's what you are going to do, and then you plot ai versus omega I. That is our amplitude Fourier spectrum. So ai versus omega I. So something like that. What does it tell?
This scales
That in this range there is frequency. So this range is important. And if your structure is lying in this range,
then it is going to damage.
then you will have more damage in your structure. Okay, there is not one frequency. There are several frequencies. There is a band of the frequency which is causing damage to your structure. Okay, but suppose your structural frequency is somewhere here or here, Either your structure is very rigid or very flexible as compared to this. Okay. So actually this advantage we take in case of base isolation. So in base isolation what we do? We increase the period too much. So the frequency reduces. So frequency of my structure is here and that of the predominant frequency band of the earthquake is here. So my structure is affected very little. Only this much amplitude is affected. On the other hand, if it was fixed base, let us say here, it would have been subjected to this much amplitude.
So the response spectra will identify different frequency and plot.
No. We are not yet talked about response spectra. I am talking about Fourier spectra.
Sorry, Fourier spectrum will identify different frequency and give the plot between amplitude and those particular frequencies. If there are 100 frequencies, there will be 100 plots and corresponding to.
Theoretically, there will be infinite.
Yes.
Okay, but this will go on reducing, and then after particular frequency, you can ignore those are not useful. So for me, the useful frequency is this. And I have to ensure that my structure, if possible, sometimes it may be possible, sometimes it may not be possible. If possible, my structure, I should design in such a way that the frequency of my structure is away from this. But in some cases it may not be possible. Then whatever effect is there, I will design for that effect. Yes.
So like you said that in base isolation we are increasing the period, so the amplitude is increasing. So for dampers we are decreasing the period, so we are going
Dampers. Now in dampers we are not decreasing the period. The effect of damping of period is little. Damp frequency reduces. Okay. You have seen, but the effect is little. So in case of damping, we keep our structure here itself, but help it in dissipating energy. Because if my structure is here, what will happen? It will impart more energy. The structure has to dissipate that energy. So the principle of base isolation and principle of supplemental damping is different. In base isolation, we are reducing the amount of energy which is imparted to my structure. Okay, so I reduce the energy input itself, but in damper, I am not reducing the energy input. Energy input will depend on the period. I am not changing the period much. Okay, and what will happen? The energy which will be imparted to my structure, I will help the structure to dissipate that energy. If I am not helping, then what will happen? The structure has to dissipate that energy. Whatever energy has been given to the structure has to dissipate. How can a structure dissipate energy? How can a structure dissipate energy? We have done so far that only in this course. How can a structure dissipate energy? Through yielding, through hysteresis. Okay. If a structure has to dissipate the energy on its own, how it will dissipate? Through this hysteretic curve. Because energy dissipated per cycle is area of the hysteretic curve. So it has to make larger and larger hysteretic curve. If energy imparted is more, it has to develop a larger hysteretic area. And how it is going to have a larger hysteretic loop? By increasing the displacement. And if it is increasing the displacement, what is happening? The damage is increasing, chances of collapse are increasing. Okay. If somehow I dissipate that energy by some other means, supplemental energy dissipation, dampers of different types, then what will happen? The structure has to dissipate less energy. And when the structure has to dissipate less energy, the size of the hysteretic loop will be smaller, damage to the structure will be small. Okay. Any other question? Okay, these two terms you are clear, magnitude and intensity, common, very common mistake. So, are we interested in magnitude or intensity?
Magnitude.
Hazard is depending on magnitude or it is depending on intensity? Magnitude or intensity? No. Hazard is intensity. So level of shaking is intensity, not magnitude. Okay. Suppose You want to read in night. I give you a 1000-watt bulb.
1000 watt bulb.
1000-watt bulb. Will you be happy? You can read easily. But I put that in the other room, not in this room. So when you have to design the lighting in a room, you never design in terms of wattage. You design in terms of intensity of light. Intensity of light is Cadillac. I can put any number of bulbs. I have to arrange, I have to design these bulbs, light fixtures in such a way that I should have enough intensity of light at this location. If I just say put 1000-watt bulb or 500-watt bulb, doesn't going to work, because 1000 I'm putting here, here or here. That will make a difference. Same thing is here. Magnitude is giving us the total amount of energy released. But where? Until unless that question is asked, that where that energy is released. And is there any wall in between? Suppose there 1000-watt bulb and I remove this wall, situation will be different. I put the wall here, the situation will be different. So what is the path which it is following? So magnitude alone does not decide hazard. Okay? So hazard is given by intensity. We are interested in the intensity, not magnitude alone. This is another thing, that the intensity will depend on magnitude and several other parameters. Not magnitude alone, some other parameters also. What are those parameters? Most important is the distance.
Soil conditions and this.
Okay, all of you have heard that story of Birbal ki khichdi? Have you heard?
Yes.
Anybody who has not heard? You have not heard? Okay. So there is a famous story. It may be maybe in south. It may be in the name of Tenali. Okay. So same story may be there in name of Tenali Ram. In North India, it is in the name of Birbal. So Birbal was the minister of King Akbar, and he is known to be very witty, and so one day one monk, or story is like this, that Akbar and Birbal, they were walking on the bank of a river, and it was very cold weather, and then the Akbar asked that can somebody stand in this water on the whole now, it is so cold. So Birbal said, yes, there are some people who can do that. So can you bring some person? So he brought one monk who was living in Himalayas in cold weather, so he has practiced that. He kept standing there, and he said that I will give him 100 coins if he is able to stand overnight. So he gave that whole. He was standing there. So then in the morning, he brought him, Birbal brought that monk to the king's court and asked him to give 100 coins. So then the king asked that, how did you manage? How you were standing the whole night? So he said that when I was standing in the river, I could see a lamp in your palace, and I focused on that lamp, and I could stand. Then I did not feel the cold of the water. Then king said, okay, then you have cheated. You were receiving the heat from that lamp, and that's why you could stand. And he denied. Then next day, Birbal didn't come to the court. 2-3 days happened, Birbal didn't come to the court. The king was worried what happened. So he went Birbal's home, asking him that what happened. So he said that he is at the river. He has gone to the river and he has not come. So then king reached there. So he asked Birbal, what you are doing? Then he said, I am cooking khichdi. Khichdi, you know? Khichdi, all of you. From south, the Pongal also cook khichdi. So what he has done? There was a tree, tall tree. So at the top of that he has put his pot. And he was burning the fire here. And he was saying, I am doing this for 3 days. This khichdi is not cooking. When it will be cooked, I will come to the pot. Before that I can't come to the pot. First I have to cook my khichdi. Then king said, are you fool? I thought you are a witty person, but you are doing such a foolish thing. By doing this, making fire here, how can you cook khichdi there? He said, so sir, then what are you? How can a lamp in your palace can keep that monk warm in the river? So this is important, that where the lamp is and where the khichdi, if you want to cook the khichdi, then the fire has to be close. Okay. So if earthquake high, what is the moral for our understanding? That magnitude is like fire which you are burning. Okay. What you are interested is in cooking your khichdi, not in the fire. So here magnitude is required, earthquake is required, but that alone cannot cook your khichdi, because it will also depend upon the distance, how far your side is from the magnitude. So intensity will vary, and it is the intensity which we are interested in predicting, not the magnitude. We are interested in predicting the intensity, or for predicting the intensity we need magnitude. Okay. So this is discussed. Then the most commonly used representation of earthquake which we have seen is none of these three. Rather we use response spectrum. Okay. So what is response spectrum? Response spectrum is obtained from response of a large number of structures. What are those large number of structures? Simple structures, single degree freedom system. So a single degree freedom system, can it represent a building? Can I use a single degree freedom system to represent a 100-story building?
No.
I can.
Yes.
If I am considering only fundamental mode, single mode I am considering. So a single degree freedom system is representing a single mode of a multi-story building. Okay. So it is not just single story building. A single story building can be represented by single degree freedom system, but a given mode, and we know fundamental mode is contributing the maximum, and I can get contribution of different modes using different single degree freedom systems. So these single degree freedom systems are representing different modes of a multi-story building or single story buildings or bridges of different heights. So you get the response of these single degree freedom systems and plot those. That gives you response spectrum. All of you know that. You have done this also. So how we obtain response spectrum, you know. And most of the times we are trying to predict this response spectrum. So rather than predicting the earthquake itself, we are trying to predict the response spectrum. So which of those three parameters it is able to represent? If I am using response spectrum, it is able to represent PGA, PGV and PGT, and also frequency constant. You agree it is able to represent PGA, PGV and PGT? This I leave to you. The answer is in A.K. Chopra's book. Okay, in A.K. Chopra's book, there is a chapter on response spectrum. Read that, and when we meet tomorrow at 4. So we will continue our discussion. There you have to explain me how this is representing PGA, PGV and PGD. This response spectrum. Okay. Yes.
Response spectrum that we are talking, we are considering fundamental.
Response spectrum we are not considering fundamental. Response spectrum is giving us the response corresponding to a single degree freedom system, which may represent any of the mode of a multi-degree freedom system.
But sir, if we have a building that is irregular in elevation, so we cannot plot the response spectrum for that to this.
Response spectrum we can plot only for single degree freedom system. We cannot plot for multi-degree freedom system. If you want to determine the response of a multi-degree freedom system, first you have to determine its different modes. Corresponding to each mode, you will make one single degree freedom system. You will get response of each single degree freedom system corresponding to each mode of the building, and then you will combine to get the response of the actual building. So it's not that response spectrum is giving us response of the building corresponding to fundamental mode alone. It is giving us corresponding to each mode. You have to know the method of combining both, which now you already know. Okay, mode superposition. So in mode superposition, what we are doing? We are obtaining response of the building multi-degree freedom system in different modes through use of response spectrum. Okay, and then we are combining it. Okay, any other question? So we will stop here. Tomorrow we are meeting at 4 and we will continue our discussion from here. And you have to tell me